In this example, I'll show you another circuit and I'll try to solve it using current division and some simple simplification, resistor simplifications. So in here we have one source, and that's a current source. That's an independent current source, and 1, 2, 3, 4, 5 different resistors. And what we're asked to compute is the I naught in here and the V naught in here, and also the power dissipated in the 6 ohm resistor. So there's multiple ways to go around it, but what we will do is we'll use current and voltage division. Well, current division, I can't apply it readily because current division applies to resistors connected in parallel. So this is not connected in parallel to anything. These two are connected in parallel, that's for sure. These two are connected in series. So I'll have to do a little bit of simplification. So I'll highlight the simplification I'm about to do. So I believe we should be able to simplify these two resistors into one resistor because they're in series. They'll become like 30 ohm. And we can simplify this and those in parallel, and then we combine them with the 6 ohms in series. The resulting 10 and 9 in parallel will the resulting will be in series with the 6, and we'll have two resistors. And let me just redraw that circuit and do the computation. So I went ahead and drew that circuit, and I zoomed out a little bit so that we can see them. So what we have is these two in blue, the 10 and 20 become 30 ohm. That's this resistor in here. And these three became 10 and 9 in parallel with a series of 6. It became 15 ohms, so that's here. So do we know, or do we have any of the original currents? Well, as it turns out that this I of O, for example, because we combined these two in here, it disappeared, so we can't see it in this equivalent. And the same with a V naught in here. We can't see them because we combined the 10 and the 20, we can't see it. So now we take a look at that. I believe we should be able to apply current division in this particular circuit, even though it doesn't look like it, but these three are in parallel. You might be able to see it a lot easier if I actually redrew that circuit like this, for example. We can do this here. So this is the blue resistor in here, and this one here is the red resistor. I can rearrange them. It's exactly the same circuit, and you can apply current division for it. So this is a 2.4 amp, and this happened to be R of A, and that's basically just 30 ohms, and this is R of B, and this is 15 ohms, and we can figure out the different currents going through it. So for example, let's assume that we get this one here, we call it I of A, and this one here we call it I of B. Okay, and I can highlight them in here. That's I of B, and that's here is simply I of A. And we can use these I of A's and I of B's. Let me just make sure that we understand where they're coming from here. So this one here, I believe it becomes I of B, and this one here becomes I of A. That's basically, they're the same currents that we're about to compute. Okay, so let's do that. Let's do the computation for them. So the computation for I of A is simply, it tells me the I of S times the other resistor, which is R of B divided by R of A plus R of B, which is simply 2.4 times R of B is 15 divided by 30 plus 15, and that number would be 0.8 amps. Okay, so that here is 0.8 amps, 0.8 amps. Okay, and we can just say that this here is 0.8 amps. That's basically the I of A. All right, we can do the same type of things for I of B. We can either apply, well, 2.4, 0.8 goes to I of A. That means the rest goes to I of B, but we can apply that it's 2.4 times 30 divided by 30 plus, I believe this is 15 in here. Okay, and that number will be 1.6 amps. Okay, so that here, let me just highlight it. This is equals 1.6 amps. So this one here is 1.6 amps, and this one here is equal to 1.6 amps. All right, so now that we know all of this, I believe we should be able to figure out everything we need. So for example, the I naught in here, well, yes, I couldn't use the 2.4 as a source to split between, or to divide it between the 90 and the 10. However, now I of B is basically my source for the 90 and the 10 because it gets divided between the 90 and the 10. So I can apply voltage division rule in this particular case and figure out what I naught is. So I write that in here. So here's here. So you can figure out I naught is simply the I of B. Okay, I of B times what I'm interested in is actually, I can substitute it with numbers. I think it's just faster. Okay, so I of B is just simply 1.6, and what I'm interested in is the one that is going through the 90. So I'm going to take the 10 and put it in the numerator. 10 divided by 90 plus 10, which is simply 0.16 amps. Okay, And we can do similar analysis in here to figure out what the V naught is in here, for example. We can figure out the V naught using multiple ways actually, but if we just apply Ohm's law tells me, well, I know the current and I know the 20 ohms. I can figure out what V naught is. Well, V naught happened to be here. So V naught will be simply the positive of 0.8 amps times 20, which is simply 16 volts, I believe. We can also use voltage division to figure out what the value of V naught in here is. Of course, I need to figure out what the voltage between here and here, which is the voltage across this particular current source, which if I go in here, I should be able to compute. This is this voltage across the R of B, or this voltage, so I can use this current and that particular resistor, or the 1.6 and this particular resistor, figure out that voltage is. Actually, let me just compute that. So I'm going to call this plus minus V. This is plus minus V. This is the voltage across the current source. So plus minus V, or I can call it Vs, for example. So V source. Okay, that will be simply the same voltage as 1.6 times 15 ohms. And that's 24 volts. So there's 24 volts. So I can say, well, this 24 volts, that one here, okay, I can say that this particular 24 volts gets divided into between the 20 and the 10, and I can apply current division rule or voltage division rule to figure out that V output. So I can say V output is just simply the 24 gets divided between the 20 and the 10. And you can compute it. Hopefully we'll get that 16 volts. And yes, we do. That's 16 volts. Okay, it's the same type of number, but it's just we use current voltage division to do that. Now, the question is also asking us to figure out what the power dissipated in the 6 ohms. Well, I know the current going through it, so that's pretty straightforward. I have 6 ohms and I have 1.6 amps, so all I have to do is just basically substitute in the values that I have. Okay, so let me just do that. So the power in the 6 ohms, is simply 6, or well, I can substitute it as 6 times I squared, and that I happen to be 1.6 squared. So 1.6 squared, and that will be, I believe it will be probably 15.36 watts.